Hi, my name is Roland. So in the last couple of months I've been building my AC Powerwall, and now is the time when all the testing is finished and we can speak about the challenges which we had in the past. Today's part is all about software, and for those of you who say, okay, the software, that's not my thing, I'm no coder, programmer, whatever, still bear with me just a little bit, because everybody is of course fluent in using phones, apps and stuff like that, and I will just show you the latest iteration of the monitoring app, and thereafter we will go into some details of coding of the microcontroller. And yeah, there's a lot of pitfalls I can tell you about, and if you already have some experience in programming of the Arduino IDE, or maybe you just started and you could have some interesting moments here in this video also. Okay, let's see the app. This is the last iteration of the Blynk Monitoring App, which I have set up for the Powerwall. So when you open an account in Blynk, you are getting some initial credit. They call it the energy, and every of these different kind of indications, they cost some credits by creating it. For the first try which I had, I just used the free credits, and that gave me 10 indicators, and then I bought 1,000 credits, which relates to another extra 5 of these indications basically, and that has cost me about 3 euros. So what do we have here? We have now 4 LED indicators. So this is showing the charges. Now both are activated, the inverter is off, and then here's a fourth one which is charger lock, called the charger lock. So when the Powerwall is basically reaching near the full condition state of charge, then one of the charges will be locked, and only one will then finish the job. Then I have the gauge, which is graphically showing the state of charge, and then some just values, the mode, then the millis timer, which is showing how long the control is running since the last time it was started, and battery voltage. And here in the middle part, this is phase 1, phase 2, phase 3 readout from the smart meter. And then I told the Powerwall which one is the active phase of this, and in my case it's the phase number 3, and this one it takes over here for doing its internal calculations for the average power in the last cycle. And here underneath is the inverter watts. So if the Powerwall is changing from charging to discharging, we will have the readout of the inverter there. Then we have the temperature there at the moment at the controller inside the cabinet. Well, that is how I did the monitoring, and it's working pretty nicely. But please stop before you go. Let me tell you what the controller actually can do. So we have 2 metered modes. The first mode is called avoid import. So it will try to, when it's charging the battery, really not to touch the grid so much. And the second one is allow import, which is kind of just putting the trigger into a position where some part of the energy which is ending up in the battery could also come from the grid. Then the third mode is a pure timer mode. You can set 2 timers, and so for each charger and also for the inverter. And it's just, you don't need a solar system in this case if you want it. It's just taking time-based power. The fourth mode is a mixed mode, so you can meter during the daytime, for example, but then also set a timer for off-peak time and during the night, for example. Then the next 4 modes are all manual modes, so you can manually switch on the charger number 1 only, charger number 2 only, and the third mode is 1 and 2, and the fourth mode is then discharging using the inverter. And the last 4 modes are setup modes for the timer, then limits, parameters, and the clock. So about 40 parameters can be directly set up at the controller, so there's absolutely no need to be involved in programming. So even you just run the controller the first time, you just go through all these setup menus and fill out the fields, and the controller knows what it is expecting. Yeah, so that's more or less about software for those of you who do not want to be involved deeper into the matter. So thank you for watching this episode, for those who don't want to continue. And please check up if there are some more videos coming in future, and I see you then later. And for all the other ones, please join me now for a little bit in-depth view into the coding. Thank you. So first of all, let's just speak shortly about the basics, what we are dealing with in this project. So first of all, we are using GPIO pins, so reading out positions of switches, mode selector switches, the rotary encoder, stuff like that. And then we are using 2 of the 3 serial port communication ports of the Mega. The port number 1 is used for the Modbus, and the port number 2 is used for the Wi-Fi. And then of course we are just using the standard I2C communication. There's a lot of modules which are using I2C, so we have 2 displays, and we have the analog to digital converter and the real-time clock. They are all using the I2C. Then we have the SPI. SPI is used for the SD card reader and writer. If you now mix up this many communication protocols, there are some real challenges coming with it. When let's for example speak about the Modbus. The Modbus was programmed, the library, from a guy who had some interest to do some project for himself, and he left the library there for everybody else to use. So it might have been quite good in his case, but if you use other ones' libraries, there can be some challenges in your project. And we had some. I can tell you at least 2 stories which have been really challenging with the Modbus. And the other things like the Blynk app, Internet of Things, communication and server protocol company, right? They have their own set of instructions, and they will tell you what is the optimal way to use their code implemented in your project. but this might not fit as well to your case, because you will see all these kind of communications. Everyone wants to kind of be prioritized and have a high level of integration into your system, and will be kind of dominant against the other one. And what you now have to find is a balance, and it's really a very, very thin line, which you have to find that all of this works, right? Because if you make, let's say, the monitoring, the Blynk monitoring, if you give that one too much space, the Modbus will not work and it will start dropping values. You will not get the return what you are expecting there. The standard like I2C works pretty well, so those kind of things are already supported from the people and the companies who make those breakout boards and stuff like that. The libraries are there and they're usually functioning. I had problems, for example, with some freezing displays, but that was on the prototype. You know, the connection's very bad there, and if there's some commands dropped, it could have caused the controller to freeze, right? So the biggest challenge was, first, before I did not have Wi-Fi, was Modbus. There was one case that I just could not read out and use the data which was presented to me easy enough to use it in my code. And the second case was something kind of similar. I was trying to read out, right, the power of 3 phases, and it turned out that every second read request was dropped, right? And you have to, sometimes you need so much time to understand what is actually going on, and then once you kind of see, oh, this is happening, then you can find tricks and write your code around this problem so that you really then achieve what you actually wanted. So the other problematic is that some of the libraries, they require an interruptive timer. So I only have one timer in use for all the software, for all the code, and this is the Modbus. So because the library is written like that, so my interval of reading the smart meter is 5 seconds, and the Modbus timer will exactly after 5 seconds will kind of interrupt everything else what is going on, and it will get his data. This can be a problem somewhere else, of course. So I tried to, all other functions are kind of written really gently into the code. So they will just wait until this part is done, you know, and then if there is time, they will then do whatever they have to do. The Blynk app is also extremely dominant. If you would use the syntax like they say on their website, it would basically also stop everything else working, right? Blynk requires something like a command which is kind of keeping the connection alive. And they actually say you have to put it into the loop. So every time when the loop starts, that command should actually be sent to the server so that the server knows, okay, I'm still here, I keep this connection alive. But if I would do that, it would kind of block out Modbus, because Modbus is the same thing. The controller asks the smart meter, please can you send me your data, and until the smart meter would return the data, the Blynk app would already have more or less interrupted everything. So this part I had to solve, that I really tried to find a limit how long time can pass until I send a live signal to the Blynk server and it does not disconnect the connection, right? So this is somewhere, the limit is somewhere around 10 seconds. So there's no need to actually activate this every 1,000 times a second, right? In every loop. That's absolutely not the case. So in my software now, I'm talking to the Blynk server once every 3.5 seconds. I send him the signal, hey, I'm still here, please keep our connection. And you know, so this kind of things you have to find out by yourself. If you read forums and how other people solving problems, this might be a perfect solution for whatever they did, but it might still not work in your case. So it's always finding the balance. You give one function more weight and you will see the other one is going out of control. So you always have to check every end, whatever you are doing. Then a lot of time actually I have spent in kind of optimizing the state of charge indication. You know, the state of charge indication on the controller is based on the voltage readout, which is usually for batteries okay, and also for lithium ion batteries is okay, but for the lithium iron phosphate chemistry this is really a headache, because you know the discharge curves in lithium iron phosphor is really extremely flat. The hardware is good enough, right? The 16-bit ADC is perfectly suitable to read those voltages, but lithium iron phosphate, when you change between the charging, discharging, resting, lithium iron phosphate, the chemistry does not maintain its voltage when you release, right? It is always trying to go back to a resting state, and so this is of course a challenge, but you know and you can predict what the battery will do, but the controller needs to have memory, right? And I mean memory, you're not storing something somewhere, it's just that during the day the controller is acquiring so many data, so many variables are filled with some data, that it's short time memory, so it knows what it has actually done 5 hours ago or whatever, right? And so it knows that the battery is now resting, or the battery, let's say the charger, last time it has been activated, that's 10 minutes ago, so the battery is somewhere in between charging and full resting, or with when you're inverting, when you have the load on the battery, it's always important to check the actual current, because this will result in the voltage drop, and this will then also kind of translates in state of charge. And this is also always in lithium iron phosphate, there's also a time component always included, right? When has this happened last time? When has this happened last time? Is it a short period? Is it long time ago? And when something is long time ago, the curve is somewhere different, in a different place than you would expect it when something just happened before. But that is no problem. The controller knows this, right, during the operation, The only time when it does not know it is when you would reset it, right? When talking about resets, you have to know resets happen. Not critical in this application because, you know, when the controller powers down, all the relays will power down, so this will bring all charging to stop, inverting to stop, whatever, so the Powerwall will basically go down also, and when after the controller restarts, it will not directly restart with activating charges or whatever. It will first take the first charging cycle to access the situation, and then it will start to be active. So it's not a dangerous situation when the controller goes down. It's just forgetting everything, right? What I said before. What is bringing the controller down is mostly related to internet. So you have disconnects of the Wi-Fi, disconnect of the internet to the ISP, to the service provider. You know, the code is actually written to kind of see those disconnects before it tries to call up some data from the server or whatever. But it does not always work like that, and some of those occasions slip through, and when something slips through, the controller would basically stop, it would hang. But to prevent a controller to hang, we have something called a watchdog, which is activated in that moment, and when the watchdog does not get a signal for, in our case it's the maximum available time of 8 seconds. So if there's nothing ongoing in the controller for 8 seconds, the watchdog will kind of reset everything, right? And start from the beginning. And yeah, those things, they are always related to the internet, to Wi-Fi and stuff like that. And in my situation here, I seem to have a little bit unstable connection to the internet service provider. And when this happens, it mostly catches the controller kind of in the action, and it will reset. So when I started to implement the monitoring, right, it changed from one day to the other. You have your internal stuff running and it works very well, and then you go to the external stuff like Wi-Fi, internet, servers, and it just changes completely the situation. In the bad days I had up to 10 resets a day, right? In a good day maybe 3, and I was writing around in circles. You know, you only have like 5 commands there which you can use. Blynk is the problem that Blynk is responsible for the library, right? The Blynk library is responsible for everything, right? For initiating the Wi-Fi communication, building up the connection, and then building the connection to its own server and this stuff. So you cannot kind of use other libraries to just look over your Wi-Fi connection or this and that. This is all managed by your Blynk library, and at the end you only have like 5 commands available, and the first one you cannot even use. If you try to start the connection with the simplest command, right, which is blynk.begin, that is a blocking command. If the Wi-Fi connection is not present when you start up with that command, the controller would already hang up. So you cannot use that. So you have to go the little bit more detailed way to start the initial connection, and And then you only have a couple of commands which check about is your connection still alive, and then you would call up your data transfer and this kind of stuff. But it's always when you have a reset, you know, okay, it came from the Blynk. How can I say that it come from the monitoring? Well, if I deactivate it, you can start the controller by not using Wi-Fi, not connecting to Wi-Fi. It's very easy. You will start the controller and then you push the encoder button and it will basically jump over the part of the internet connection and it will be offline for as long until you again reset the controller. Or it can be completely deactivated from the setup also. These are have been the main challenges. We can then go a little bit into the code and I show you how the controller is setting up itself and then what are the main things in the loop. So the code and also some libraries which I am using, you can find in my GitHub repository. It's under my name, Roland and AC Powerwall. You will find the link in the video description. You can download and then look into it. You can use the Powerwall file also to just take out some code for your stuff if you need it and if it helps you with your programming. I have absolutely no problem with that. The latest software today was basically version 1 for the new controller, the version 2 controller, and this was uploaded before and running the Powerwall at the moment. And inside the explanation here in the readme file you can have a full description of the system, what kind of components are used and what it actually does, the controller, and what the logic is about and what is used for monitoring. Let's look into the IDE. We will not talk about the whole stuff. Of course, the sketch is extremely long, of course. We just briefly take out some important items and talk about the general structure, which of course is starting with all the definitions and global variables, and about those we will of course not talk. Here one interesting part, this is the definitions about the Modbus, and this is one thing which I told you, which is very interesting. So this library I could only make working, so I wanted to read the power of phase 1, phase 2 and phase 3, and to get this, to achieve this, the library is actually dropping every second read. So I'm reading power 1, then I'm reading something completely unrelated, right, which I don't need because I know this one will be dropped. So I call it a dummy read. Then I read the power 2, then another dummy, and then the power 3. So I have to read 5 things to get my 3 values of interest out of it. You know, it takes really a lot of time to find out the problems and how you can kind of circumnavigate it, and that can really suck sometimes. In the setup we are starting with the EEPROM read. So after you finish setting up your controller, everything will be stored in the EEPROM, and when the controller is restarting the next time, it of course knows what you put inside your settings, and at the moment it's about 40 variables which are stored there. Then comes all the typical standard starting stuff of the modules, breakout boards, and this part is the Blynk and Wi-Fi. So you can avoid all of this by pressing the encoder switch, and if you don't, then the ESP will be activated and the Blynk will try to establish a Wi-Fi. So it's a two-step configuration in this case, because this one does not block the controller if there is a problem with Wi-Fi. Yeah, the loop, other than the Modbus, which is timer based, the rest of the loop is actually based on timestamps by millis. So I'm putting time intervals for every of these functions, but the starting point is not exactly defined by a timer. It is just saying, okay, if so many milliseconds have passed, when you have time the next time after so many milliseconds have passed, then please do this point. So please check for which mode is activated, where the switch is standing, and then do the mode if that time is passed, etc., etc. So it is non-interruptive. Non-interruptive loop is very important in this case, because if you put interrupts into this, you will destroy Modbus or whatever. And Blynk in the loop, I'm trying to catch actually disconnects of the Wi-Fi. So before this is the blink.run is actually checking if Blynk is alive, and this is only done if Blynk is connected. So I'm trying to catch it, but it's not always possible. Sometimes the controller will still go into a reset. The reset, here you see always watchdog timer reset. So this is actually resetting the watchdog timer, but if there is a hang, it cannot reset the watchdog timer, and then it will reset. So what are the functions inside the loop? So after Modbus comes reading out the position of the mode selector switch and showing this on the OLED display, and then going into the subsequent mode itself and do the mode. And these are the, you see, normal modes, they are timed, but here you have 4 modes. These are the setup modes, which don't have any kind of timing, and this is because setup modes need to be entered really every time when the loop is running because of the rotary encoder switch. So when you change modes and turn on the rotary encoder, you of course want to catch every single turn and movement of the rotary encoder. Next timed is LED signals and checking about the temperature, activating fans. This was Blynk and the transmission of the Blynk data. Then we have the current acquisition. This is when the inverter is running. Every 20 seconds the controller will then check the output of the inverter. Here we have a reset function, which can be deliberately called. Some setup modes are resetting the controller after the finish, or you can also set a daily reset if you want it. Then comes all the modes. We will just skip this. So here, for example, we have a setup mode, And for the setup mode, it's important to say that you are not allowed to every time, because every time the controller is calling the loop, you would actually try to show all the data on the LCD screen or the OLED on your screen, right? And that is not allowed to do, because that takes too much time to build up the screen information, and that would slow down the rotary encoder so terribly that it basically would not work. It would just bounce around. So when I enter the setup mode, I actually build up the screen once, and then as long as there's no change on the screen, there's also no new build up. And when I actually change only the value through turning of the rotary encoder, then I really only change that one value which is actually related to that input and nothing else. So this is keeping the loop fast, and it keeps the rotary encoder working. And after all this is done, of course, then those data is taken and stored in the EEPROM, and then either it's just returning to the mode, or maybe also completely resetting the controller. It depends if it's necessary to reset or not. Okay, then comes all the functions, displays, read encoder, signals, logging. So the data logging after every full charging cycle, which is about 6 minutes. I'm also saving all this logging data to the SD card, so that then I can actually analyze it on my computer. Blynk, if it kind of finds a disconnected situation, it tries to connect again. And this here is the data transmit from Blynk. And here is also important to say, in the when you transmit Blynk data, they say you should not send more than 10 values at once. So I split it. I have actually 15 values to send, and I split it in two, and the millis is always part of it, so I split it into 2 times 8 values which I'm sending. So every 7 seconds goes one part, so every 14 seconds is basically one loop for the Blynk data. The current sensing is working, as I said, every 20 seconds. I am sampling the output signal of the inverter, and it takes about 200 samples, and from the peak difference, maximum to minimum, is then calculated the amperage of the output. The fans are running as soon as you reach the set temperature, and when the temperature goes below, then they still continue to run for about 1 minute, and then they will shut down. All the calculations, voltages, there's a lot of functions going on. And the longest one is, of course, the state of charge, but this is only because of the chemistry of lithium iron phosphate is so extremely intense to predict. And there's, you see, tens of if-then sentences, conditions to be, with two charges. This is the charging, right? What happens when one charger? What happens with the other charger? What is when both chargers are on?
what you have to correct when it's inverting. How do you correct that? That's right. And then comes basically the voltage curve. There's only one voltage curve per chemistry, which I put. It is basically an early resting state voltage curve. So after charging, charges off, then 1 minute resting, and then I read the voltage, and the voltage is then translated to a state of charge after all those other corrections are done. So if you compare to a column meter in parallel, the state of charge will usually be somewhere inside 5%, but the most difficult part is this middle part of the discharge curve, which is extremely flat. So it is very easy for the controller in the low part and in the high part to tell where it exactly is. And so according to those, if you want to reset your column meter, then you can actually do that easily by the controller when the state of charge is very low. Well, that is the programming at the end. This is all Modbus.
Right, it became quite a long talk, and I hope there was some interesting information in there for you. But I think it's time to end this video. If there is any questions left, please give me a comment, and maybe I can give you some more details where there's a need to. Right, I would say thank you for watching this episode. Please look up the playlist for other videos which you maybe did not see yet, and it always helps if you maybe press like and subscribe if you didn't yet. There will be probably another video coming out explaining why I actually do not balance the pack. I saw that the interest in those kind of videos is quite big, and maybe I should give my thoughts about it too. Okay, then, so thank you for watching, and I will talk to you soon again in the next video. Bye.